Hello, everyone. Today I'm going to continue the Calculus 1 and 2 lesson review. And now we're going to start Unit 2, which is differentiation, the definition and fundamental properties of differentiation. So this unit introduces the concept of differentiation and provides several properties regarding the derivatives of fundamental functions. So the first part we're going to talk about is the definition of a derivative. So essentially, we're going to talk about what secant and tangent lines are. So a secant line is easy to visualize. Is just a line between two different points. So if we have the function f of x here, you can see 2 points that the secant line intersects, a and f of a, and x f of x. And they are at the different x values of a and then x. So what happens when we bring this point here, x, very close to a? So that's what we can see here. So you can see that at point, this is the secant line still, but this is the first point that we have. We want this point, x1 and f of x1, to very closely approach a f of a. So we get there very close. So the second point we reach just casually is just x2, f of x2. Yeah, it can be, this point, second point can be any point, but just along this curve, but this is just to represent that this point is getting very close to a f of a. And then once in this line right here, from a f of a to x2 f of x2 is still a secant line because it connects to it intersects 2 points on f of x. But when we actually reach a f of a, then we get a tangent line. And a tangent line is a line that intersects only 1 point of a function. And see, it only intersects a f of a right here. So we're going to talk about rates of change, the different types of rates and change that are important for functions. So the first line we're going to talk about here is the secant line. And this essentially is the average rate of change of a function, f of x, between two different points. And the slope of this secant line is just your average y2 minus y1 over x2 minus x1. Just a regular slope between two different points. You learn this in Algebra 1, and this is coming back here. So yeah, the secant line is very easy to visualize and very easy to understand. And since we're going to talk about f of x here, we can just say that the slope of the secant line is just the change in f with delta f. So delta just means the change in. So the change in f over the change in x, or otherwise known as delta f over delta x, equals f of x minus f of a over x minus a. And essentially this is the y value, the second y value minus the first y value over the second x value minus the first x value. And just to understand, the rate of change is how fast the function is changing. So between points a and x, the function is changing at a rate of this slope right here. Now we're going to talk about the tangent line. And the tangent line is known as the instantaneous rate of change at a function. And you can see that it only occurs at 1 point. So the slope of this function, or the tangent line, is the limit as x approaches a of f of x minus f of a over x minus a. So essentially, it's the limit as these 2 points converge or come together, and essentially Yes, if they come together, then this limit will become undefined. But if you get the points very close to each other, you'll get this tangent line of this function at this point a f of a, and then this is the rate of change again. So we know that the slope of this tangent line, and you can think of it as the slope of the limit as x approaches a of the slope of the secant line itself, because as this point gets very close to the point we're going to, it's still a secant line until you approach this the point itself. So until x approaches a, you still have a secant line. And you can kind of represent the tangent line as a secant line very closely though. So let's just change the slope a little bit just so it can be, you can work with it easier. So if we set a minus x, if we set a minus x as the change in x, we could just substitute this value here, the change in x, for x minus a, or x minus a, or a minus x actually. And that would mean that if x approaches a, then the change in x approaches 0. So we just substitute that here. And this limit will become this new limit here. The limit as the change in x approaches 0 of f of x plus the change in x minus f of x over the change in x. So this is essentially the same slope here, but we just manipulated it to include the change in x instead of just x minus a, which is still the same thing. And if we just set the change in x as the letter h, then we can set this value here, and we can just substitute h for the change in x, and then you just get the limit as h approaches 0 of f of x plus h minus f of x all over h. So we will be using this definition as the slope of a tangent line here of a function. So what exactly is a derivative? Well, the derivative is the instantaneous rate of change of a function at a specified point. So remember, the instantaneous rate of change is the tangent. You can think of it as the slope of the tangent line of a function at a point. So right here, this slope, or this value here, would be the derivative itself. And essentially, the derivative is how fast the function is changing at a single point. So like the secant line, the derivative just determines how fast the function is changing how fast the function is changing instantaneously or at a single point in time. So there are different notations that you can use to signify the derivative. So there's the Leibniz notation, and you could just see here. There's dy over dx, so or like a change in y over a change in x, or you could just do d over dx of f of x. They both mean the same thing, where y and f of x are the functions itself, and x is the variable that we're talking about. We also have the Lagrange notation, and you could say this as y prime or f prime of x. So essentially, you could say the derivative of y with respect to x, f prime of x, the instantaneous rate of change of f of x with respect to x, and any of these work, and it's just up to the whatever preference you have. You could just use any of them. It essentially comes to convenience, but both of these notations work fine. So let's review the rates of change that we've gone over. So we have the average rate of change, or also known as AROC. And the formula for the average rate of change is f of b, f of b minus f of a over b minus a. And this occurs between 2 points, x equals a and x equals b. And we're assuming that a is less than b. So yeah, a is less than b. And this is most associated with secant lines. The instantaneous rate of change, however, also known as IROC, this is the definition of the instantaneous rate of change. And the instantaneous rate of change, remember, is the derivative. So we can set this is the definition of the derivative right here. The derivative of f of x with respect to x is equal to the limit as h approaches 0 of f of x plus h minus f of x all over h. And this occurs at one point a. So right here, we didn't signify a certain point, we didn't signify a certain point, but you would substitute a for x. And that will be the derivative of f of x at the point x equals a. And this is often associated with tangent lines. So let's find some example right here. What's the derivative of x with respect to x at x equals 1? So remember that x is a straight line, is just a straight line with a slope of 1. Regardless of what x is, the slope is 1. And you can find that out like due to like it's basic algebra, and the slope of any linear line is just, the slope of a line is constant, and the slope of x is just 1. So let's use the, to find out this value right here, let's use this limit, the derivative definition, and plug it, since we have x equals 1, we're finding the derivative of x at x equals 1. We'll just substitute 1 for x, and we'll substitute x for f of x here. So I just combine those both in one step, and then you get 1 plus h minus 1 all over h. And now you can solve for the limit right here. So these two lines cancel out. The ones cancel out. You get h over h, and then that simplifies to 1. And the limit as h approaches 0 of 1 is just 1. So therefore, the derivative of x at x equals 1 is 1. Or in other words, the instantaneous rate of change of x at x equals 1 is 1. Now let's find the slope or the derivative of x squared at x equals 2. So this is a little harder to visualize, but we'll work this out. So using the derivative definition here, you can substitute x squared for f of x, and we can substitute 2 for x. So you get 2 plus the limit as h approaches 0 of 2 plus h squared minus 2 squared all over h. And that just gets you, using the binomial, like just expanding this binomial, you can get 4 plus 4h plus h squared minus 4, because 2 squared is 4, and then 2 plus h squared is 4 plus 4h plus h squared. So you can cancel the 4s out here, and that's what happens here. And you can see that the numerator in this limit here, the numerator and the denominator have a common factor of h. So you could just simplify that and take out h from both the numerator and the denominator. So doing that gets you the limit as h approaches 0 of 4 plus h. And solving for this limit, you just set h equal to 0, and you get 4. So therefore, the derivative of x squared at x equals 2 is 4. Or in other words, the instantaneous rate of change of x squared at x equals 2 is 4. Or, and if you think about it in terms of the tangent line, the slope of the tangent line of x squared at x equals 2 is 4. So let's look at secant and tangent line equations. So how would you represent the secant line and tangent lines in terms of the function itself? So f of x. We're mainly going to use point slope form for this. And if you recall, this is point slope form, y minus. So if you have a point x1, a y1, you have this point slope form, the equation for the line between, if you have a point x1 and y1, and if you have the slope m, then you can just use the point slope form, and that'll get you y minus y1 equals m times x minus the x1. So using that equation, you can find the equation for the secant line and the tangent line. And this is the equation for the secant line, the point slope form. So the y value we're going to think about is f of a. The x value is a. And the slope, of course, is f of b minus f of a over b minus a. Or so this basically uses the point a f of a, but you can also use the point b f of b. And this is just the other point that you can use, the other equation. So either of these points work, either of these equations work, and they are the same equation. The tangent line, however, uses this equation, y minus f of a equals f prime of a times x minus a. So since it's only at one point, we're using a f of a. And the derivative f prime of a is, remember, the derivative of the function at x equals a. So that's what we'll use as the slope. So what we're going to talk about the derivatives of the fundamental functions, the main functions that are important for calculus, that are important for calculus or mostly any math. So the first function we're going to talk about is the power function, or x to the n power. So the derivative of x to the n with respect to x is just n times x to the n minus 1 power. So you just bring this constant over here, n, and then subtract 1 for the exponent. This is also referred to as the power rule, and it's a very important form of derivative that will be used a lot. So the constant function, which is, we'll just say that this is 1. The derivative of 1 can be thought of as, so 1 is just the same as x to the 0, because any non-zero number to the power of 0 is always 1. So the derivative of 1 with respect to x is always 0. So let's think about this in terms of two ways. Let's use the power rule. So if we have x to the 0 power, the derivative of that is 0 times x times 0 minus 1. And anything times 0 is 0. So that means that the derivative of 1 is just 0. But if you think about it in terms of the graph, any constant function, especially f of x equals 1, the slope is 0. So you can automatically assume that the derivative of 1 is 0, because the y value is not changing regardless of the x value, and the slope of this line right here is 0. So the slope of the derivative of any constant, or we're going to talk about 1 here specifically, is 0. And this is a special case of the power rule, as we've seen before. So let's just prove why this rule works. So let's just use the limit definition here. So the derivative of x to the n with respect to x is the limit as h approaches 0 of x plus h to the n power minus x to the n power all over h. So if you recall the binomial theorem, x plus y to the n power can be expanded into this enormous sum. So this is the simplified sum here. But it essentially just becomes x to the n plus n times x to the n minus 1y plus whatever all of these are. So it just this is just a way to rewrite x plus y to the n power, and we'll be using that and we'll substitute that for x plus h to the n power. And recall that this thing here is n choose k, where n choose k is just equal to n factorial over k factorial times n minus k factorial. And a factorial is just, so n factorial is just n times 1 times n minus 1 times n minus 2 all the way to 2 times 1. So essentially it's just the product of all integers below n and greater than or equal to 1. So now we have all those facts. We can use that to solve for this limit. So substituting the value for x plus h to the n power, we have x to the n plus n times x to the n minus 1 times h plus n times n minus 1. This is just n choose 2. So yeah, don't worry about that. Times x to the n minus 2 power times x h squared plus all of these stuff. And then it ends with n times x times h to the n minus power plus h to the n power. And then we have this x minus n power here that remains. And then we have the all over h. We shouldn't forget this h. So now we can just cancel this x to the n power here on both sides. And then we just get this, we're left with this limit here. I noticed that all of these terms in the numerator have a common factor of h. And you can see here, there's h here, there's an h here, h here, and h here. And also the denominator has a common factor of h. So you can simplify that by eliminating an h from both sides. And you get the limit as h approaches 0 of n times x to the n minus 1 power plus all of this. And recognize that this term doesn't have an h, but all of these terms do. And since h is approaching 0, we could just say that we could just substitute h. We could substitute 0 for h. So that's what we get here. And 0 times anything is 0. So after that, if you just simplify all of these, you're left with n times x to the n minus 1 power. And that's how you get the derivative of x to the n power, which is just n times x to the n minus 1. So let's just use an example of the power rule here. So the derivative of x squared. So we've had an example of this before. We specified it at a specific point, x equals 2. But what if we want to find it for any regular point x? So this derivative right here will simplify that, and you could just plug in any value of x to find the derivative at that point of x. So we have this limit here, x plus the limit as h approaches 0 of x plus h squared minus x squared all over h. So the x plus h squared can be easily determined. So that's just equal to x squared plus 2xh plus h squared. And then you have this negative x squared here. Don't forget about that. So we can cancel those two terms right here. And then you're left with the limit as h approaches 0 of 2xh plus h squared all over h. And again, all of the terms in the numerator and the denominator have a common factor of h. So you can cancel h out of both sides. And then you'll get the limit as h approaches 0 of 2x plus h. Substitute 0 for h, and you get 2x. So using the derivative of x squared is 2x. So using the power rule, we can just use the power rule instead of the limit definition. And you just move the 2 here, and then subtract 1 in the power. You get 2 times x to the 2 minus 1 power equals 2x. And that's much easier. And you still get the same value too. So let's look at the values of the derivative at certain points. So you have at x equals 0, f prime of 0, or the derivative of x squared at x equals 0, is 0. You can see here it's just a tangent line here. The slope is 0, nothing's changing. Yeah. At x equals 1, f prime of 1 is 2. So you just get x. Same with x equals 0. You plug in 0 for this, and you get the derivative equals 0. That's how you get this. Plug in 1, you get the derivative equals 2. And you can see that here. The slope of the tangent line is 2. So yeah, you can just see that the rise is 2 and the run is 1. With x equals 2, however, we've seen that in a previous example, f prime of 2 equals 4. Since 2 times 2 is 4, and you can see that very closely that over here, the rise is 4. Yeah, for this green tangent line at x equals 2, the rise is 4 and the run is 1. So we could just use the power function to find out what the derivative of x squared at x equals 2 is. And it was very easy from then on. Now we have the exponential function, which is a to the x power. And the derivative of a to the x power with respect to x is equal to a to the x power times the natural log of a. And the natural exponential function, on the other hand, is just e to the x. And remember that e is just Euler's constant, which is approximately 2.71828. And this is a very unique derivative right here. The derivative of e to the x is just e to the x itself. And this is one of those special functions where the derivative of a function is itself. And this is a very special case of the exponential function derivative, where a is equal to the Euler's constant. So let's just prove the derivative of a to the x. So we have this limit right here. Yeah. So we're going to go over some facts right here. So a to the x, if we have another constant b, a non-zero constant b, or a like anything greater than, anything that's not equal to 0, if b is not equal to 0, then a to the x is equal to b to the x times log base b of a power. And also you can just use so this simplifies to, if you set b equal to e, or Euler's constant, then a to the x is equal to e times x, e to the x power, e to the x times natural log of a. And recall that log base e is just the natural log. So starting this limit, we can set the limit here. And notice that there's a common factor of a to the x power. So you could just take that out of the numerator here. And since a to the x is technically considered a constant, since h is the variable that's being concerned in the limit, and a to the x does not have h in it, you could just put the constant outside of the limit, and then you have this limit right here. So now all we have to do is just find the value of this limit and then multiply it by a to the x. Now, the way to solve this limit, you need to use the squeeze theorem, but we're not going to use that here. We're just going to say exactly what the limit is. And this limit is just approaches the natural log of a. And using that substitution, we can just substitute that here. So a to the x times this limit is just a to the x times natural log of a. And that's how you get this derivative, the derivative of a to the x here. So let's see this example here. So the derivative of 2 to the x power is just 2 to the x times natural log of 2. And these are this is 2 to the x, and these are the tangent lines at some points. So at x equals 0, f prime of 0 is natural log of 2. And it's a little difficult to see, but this slope is natural log of 2. And if you just set x equal to 0 here, 2 to the 0 is 1, and 1 times natural log of 2 is just natural log of 2. If x equals 1, then f prime of 1 is 2 times natural log of 2. And that's it here. And if x equals 2, f prime of 2 is 4 times natural log of 2. And that's the slope of this function here, or this tangent line here. The logarithm function, on the other hand, is log base a of x. And that's the inverse of the exponential function here that was shown before. And the derivative of this log base a of x is just 1 over x times the natural log of a. And this is using the natural logarithm function. So that's it here. The derivative of natural log of x is just 1 over x. So if we look at the no, never mind. So this is just a unique just a unique derivative other than the e to the x, because the derivative of the natural logarithm function, this logarithm function itself, is just a power function. Well, x to the -1 power. So yeah, it's just a very unique way to represent this derivative. And remember that natural log of x is just log base e, or Euler's constant. And this is a special case of the logarithm function derivative, where a is equal to the Euler's constant. So now let's prove the derivative of the log base a of x. We have this function here, this limit. So let's go over some facts again. So if we have a difference between two logarithm functions given the same base a, then log base a of x minus log base a of y is just log base a of x over y. So using that fact, we could just simplify the numerator to get log base a, the limit as h approaches 0 of log base a of x plus h over h, and then simplify this inside function to get 1 plus h over x. Now let's go over some more facts. Log base a, using the change of base rule, log base a of x can be changed to log base c of x over log base c of a. Given that c is any number that's not 0 or 1. And also, a constant c times log base a of x is equal to log base a of x to the c power. So this c just becomes the power of x. So using these facts here, we could just say that we could simplify this limit here and say that log base a of this function is just the natural log of 1 plus h over x. And the natural log is just a simple way to, this is a very neat logarithm to use, so we're going to use that, over h times the natural log of a. And since the 1 over the natural log of a is a constant, we'll just pull that out here. And we could just simplify this inside limit here. So with 1 over h, we can set that to the 1 over h is a constant, and since we're multiplying that constant by the logarithm, we could set that as the the power of this inside function here. So recall that the limit of h approaches 0 of 1 plus h over x to the 1 over h is just e to the 1 over x power. So we know that this is very similar to the limit of, like, that resembles the limit for e. So we can just use this back here to get e to the x. And then that becomes the limit as h approaches 0 of, yeah, so this limit right here, we could just set it equal to the natural log of e to the x, e to the 1 over x. And also recall that the limit, you could just set the limit of like this whole limit, you could just set the limit of this function right here, the inside function. And then if the outside function is continuous, then you could just set, then the whole limit will just equal to the natural log or the outside function of this limit right here, the inside limit. So in other words, since natural log is continuous for like all values greater than, for x greater than 0, you can just set the inside, you can set this limit of the inside limit here, and you get e to the 1 over x. And e to the 1 over x is generally continuous, except at x equals 0. So you could just, now you can set this limit equal to the natural log of e to the 1 over x, and then you get 1 over x. But we're not done yet. We still have that 1 over natural log of a from before. So since we have this constant here, I forgot to include it here, but we'll get, multiplying this constant by 1 over x gets you 1 over x times natural log of a. And that's how you get the derivative of the log base a of x with respect to x. So now let's look at an example here. The log base 2 of x, the derivative of log base 2 of x, equals 1 over the x times the natural log of 2. So we're going to set x equal to 1, because x cannot equal 0, otherwise this will be undefined. The derivative will be undefined. So the next best is x equals 1. And that means that f prime of 1 is just 1 over the natural log of 2. And yeah, this is just generally what the slope is. And the slope. And at x equals 2, f prime of 2 equals 1 over 2 times natural log of 2. And then that's what the slope of the function at x equals 2 is. So now we're going to talk about some important trigonometric functions. So these are the 6 main functions, trigonometric functions, that we're going to be talking about. And they're the sine, cosine, tangent, cotangent, secant, and cosecant. And these are the derivatives of each of these symbols, or each of these functions. So the derivative of sine is just cosine. Derivative of cosine is negative sine. Derivative of tangent is secant squared of x. Derivative of cotangent is negative cosecant of x squared. And then the derivative of secant of x is secant of x times tangent of x. The derivative of cosecant of x is negative cosecant of x times cotangent of x. And yeah, and these we'll be using these derivatives later. But yeah, these are important to memorize. All of the derivatives mentioned before are important to memorize and understand. So the derivative of a piecewise function, so suppose f of x is just a piecewise function with g of x at the left-hand side and the h of x at the right-hand side. It's simply just f prime of x, which is the derivative of f of x, is simply just, you could just simply take the derivative of each of these functions right here, and then that's the derivative of f of x. So g prime of x is the left-hand side, and h prime of x is the right-hand side. So for the first example, we have f of x equals x for whenever x equals, or x is less than 0, and sine of x when x is greater than or equal to 0. So what's the derivative of f of x here? Well, just take the derivative of each of these components here. We know that the derivative of, so this is the function that we have here. So it's just a very simple function, x. This is x at the, when x is less than 0. And this is sine of x when x is greater than 0. So getting the derivative of f of x gives you this. So the derivative of x we've seen before is 1. And the derivative of sine of x you've seen before is cosine of x. And this is the function that we will see here. This is the function for the derivative of f of x. So one main question that we're going to talk about in terms of piecewise functions is whether f of x is differentiable at x equals 0. So what does it mean if a function is differentiable at a point? Or what does it mean if a function is differentiable in the first place? So differentiability supposes this question here. Is f of x differentiable at x equals a? So what that means is just, does the derivative of f of x exist at x equals a? And the only way this works is whether if a function f of x is different, so if a function f of x is differentiable, if and only if f prime of x, and recall this is f prime of x that we're talking about here, is continuous at x equals a. So the derivative has to be continuous at x equals a. And so if a function is differentiable at x equals a, then the derivative itself is continuous at x equals a. This is extremely important to know, and we'll see how we can use it in this example here. So going back to this question, is f of x differentiable at x equals 0? So we'll see here that we're only concerned about f prime of x, not f of x. So let's just use the let's just find out what does it mean if something is continuous. So use the property of a continuity of a function. So let's find out the left-hand side. So the limit as x approaches 0 from the left-hand side of f of x, f prime of x, is, so the left-hand side function is 1. So the limit as x approaches 0 of 1, that's what we'll get for the left-hand side, and that's equal to 1. The limit as x approaches 0 from the right-hand side of f prime of x, you will use cosine of x because that's the right-hand function. And the limit as x approaches 0 from the positive side of cosine of x is just 1. You just substitute 0 first, and then cosine of 0 is 1, and you get 1 here. So since both the left-hand side and the right-hand side are equal, the actual limit at x approaches 0 is true. So the limit as x approaches 0 in general of f prime of x is 1. Well, we're still not done yet. The limit may exist, but we still need to find out whether the function f prime of x exists at x equals 0. But we'll see that f prime of 0 is just cosine of 0 right here. Since x equals 0 is defined in this inequality here. So cosine of 0 is 1. And that means that f prime of 0 equals 1. So therefore, the limit as x approaches 0 of f prime of x is equal to f prime of 0 itself, which is equal to 1. And therefore, f prime of x is continuous at x equals 0. And thus, f of x is differentiable at x equals 0. So that's a yes. Now let's look at this function right here. F of x equals x squared for the left-hand side, x is less than 0, and sine of x for x is greater than 0. And this is the function that we have here for f of x. So finding the derivative of f of x is simple. The derivative of x squared is 2x that we have here. And then the derivative of sine of x is cosine of x. And this is what the function for f prime of x is here. So is f of x differentiable at x equals 0? Again, is it differentiable at x equals 0? Now, notice here that there's a discontinuity at x equals 0 for f prime of x. So that means that f prime of x cannot be continuous at x equals 0. There's a jump discontinuity here. So we can know that the limits from the left-hand side and the right-hand side do not equal. So we can automatically conclude that since f prime of x is not continuous, f of x is not differentiable at x equals 0. And we can see that here. F prime of x is not continuous at x equals 0, meaning that f prime of x is not, an f of x, this should be f of x. F of x is not differentiable at x equals 0. So we can notice something about these functions here. So it doesn't matter whether whether f of x itself is continuous, but it mainly matters if f prime of x is continuous. Because look at here, both of these functions are continuous, but one is, this function is differentiable at x equals 0, but this function is not differentiable at x equals 0. So in terms of graphs and geometry, if the graph of a function f of x is smooth, like generally smooth, you can just, smooth is a relative term at x equals a, then f of x is differentiable at the point x equals a. So smooth is a general, like a relative term, but if you look at the function here, there's no disruptions in the change in f of x. It just there's a smooth transition between all the values in x and all the values in y. But in this case, if the graph of a function f of x has a, so yeah, this is what we call smooth. But if the graph of a function f of x has a cusp at x equals a, and this has a cusp here, then f of x is not differentiable at the point x equals a. And a cusp is just like a sharp turn in, or sharp change in the function value. So remember that even if a function is continuous, it does not mean that a function is differentiable. So yeah, understand that fact. So now we're going to talk about the derivative rules and properties, the arithmetic rules and properties of differentiation. So first we're going to talk about a constant times a function. So this is simple. If you have a function which is a constant c times the function f of x, the derivative of this is just c times the derivative of f of x. You could just, similarly to limits, you could just take the constant c out of the derivative, and then take the derivative of f of x itself, and then multiply by c. So it's very simple. And this is a special case of the derivative of a constant function. And yeah, it's of a constant function right here, a constant times a function. And in fact, this is basically the derivative of a constant function itself. So before we talked about the derivative of 1, but now we're going to talk about the derivative of c. And the derivative of any constant value is just 0. So let's look at some examples of this. So if we have the derivative of 5 at e to the x power, we just take the constant 5 out, and then just take the derivative of e to the x. And this derivative is e to the x. So basically, this whole derivative right here is 5 times e to the x. Let's look at another example. So the derivative of 18 times the cube root of x squared. So notice we can use the power rule since the cube root of x squared is the same thing as x to the 2/3 power. And you can just take the 18 out of the derivative, and then yeah, put it outside of the derivative and calculate the derivative of x to the 2/3 power. That will, using the power rule, you'll get the derivative being 2/3 times x to the -1/3 power. And then simplifying this gets you 12 times x to the negative 1/3 power. Now with the derivative of negative 7 of cosine of x, bring the negative 7 out of the derivative, and then you have the derivative of cosine of x. And that is just negative sine of x. So we see here, multiplying that here, but it gets you 7 sine of x. And now look at this. This is natural log of 2 is a constant. So the derivative of any constant is 0. So that's how we get it here. So now the derivative of the sum or difference of two functions is very simple. You just separate the functions itself and then add the derivatives of each individual function. So if you have the sum of f of x plus n g of x, the derivative of that is just the derivative of f of x plus the derivative of g of x. Similarly with the difference, if you have f of x minus g of x, the derivative of this is just the derivative of f of x minus the derivative of g of x. So it's very simple. Just take the derivative of each individual function right here, and then you'll get the whole derivative as a whole. So let's look at some examples right here. So the derivative of 4x plus 5. So we'll separate these two. We're going to use the property of a constant times a function and the sum rule, like the sum property. So we separate these two functions here to get the derivative of 4x plus the derivative of 5. And the derivative of 4x is just 4 times the derivative of x, because 4 is a constant. You can just move that to the beginning of the derivative and you'll get this. So notice that the derivative of a constant is 0 and the derivative of x is 1. So 4 times 1 plus 0 is 4. And that's the derivative of this whole function here. Now, this is a larger polynomial, but you can just use the same rules. Use the power rule, the sum rule, the difference rule, and the constant times a function property. Yeah, so you can separate all of these functions. So you get the derivative of x cubed plus the derivative of 4x squared minus the derivative of 6x plus the derivative of 3. For these things, for these two values here, you could just move the constant out. And that's why the 4 and the 6 are out of the derivative. And now we just have the derivatives of each of x cubed, x squared, x, and 3. So the derivative of this, the constant function, is 0. The derivative of x is just 1. The derivative of x squared is 2 times x. And the derivative of x cubed is 3x squared. And then getting you, all of that will get you 3x squared plus 8x minus 6. Now, this looks a little more complicated, but you use the same values, or you use the same properties and rules. So you notice that we can see an exponential function here and a logarithm function here. Even though this is pi, it's still an exponential function. So we can just use the properties of the derivative of an exponential function. So we can see that this is just, we'll separate this to the derivative of pi to the x plus e power minus the derivative of I times natural log of x power. So now you can just move the constant out of the derivative. So pi to the x plus e power can be separated into pi to the x power times pi to the e power, and pi to the e is a constant, so you just move that out. And I is a constant, so you could just move that out from here. And the derivative of an exponential function is just, so the derivative of pi to the x power is just pi to the x times natural log of pi. And the derivative of natural log of x is just 1 over x. So this is the derivative that you'll get here. a little complicated, but it's still using the same rules, using the simplified rules. Now we'll see the trigonometric function, like an example with that. So we have the derivative of 3 sine of x minus cosine of x. So we just separate the functions here into the derivative of 3 sine of x minus the derivative of cosine of x. 3 can go to the beginning of the derivative, and the derivative of sine of x is cosine of x, and the derivative of cosine of x is negative sine of x. And that will get you 3 cosine of x plus sine of x. Now we have the product of two functions, and this is a little more complicated, but essentially the derivative of f of x times g of x is so you first take the derivative of the first function and then multiply that derivative times the first. Yeah, okay. So essentially, I'm just going to walk this through here. The derivative of a product of two functions, f and g, is just g of x times the derivative of f of x plus the f of x times the derivative of g of x. So you first take the derivative of f of x here, the first function, or it doesn't really matter which one. This is commutative. So whichever function you take first, take the derivative of first, it doesn't matter, but you take the derivative of the first function and then multiply that by the regular function, the regular second function, and then you take the derivative of the second function and then multiply that by the normal function of the first function, and then add those two values together to get this. So this is also referred to the product rule, and I will give you some examples of how this works. So let's see here, the derivative of x times sine of x. So we have two functions, x and sine of x. So we'll just use the product rule, and that'll get you. Let's just suppose that the first function is f of x. Or no, the first function is sine of x, and the second function is x. So you just do one function times the derivative of the other function. So x times the derivative of sine of x plus the other function times the derivative of the first function, the other function. So sine of x times the derivative of x. So the derivative of sine of x is cosine, and the derivative of x is 1. So the derivative of this whole thing, x sine of x, is just x cosine of x plus sine of x. Using this equation here, a little more complicated, but we'll get through it. So 2 to the x times x squared. The derivative of that is just 2 to the x times the derivative of x squared plus x squared times the derivative of 2 to the x power. So the derivative of x squared is 2x, and the derivative of 2 to the x power is just x times, it's just 2 to the x power times natural log of 2. So getting all that together, we have x times 2 to the x plus 1 power, because we have 2 times x, 2 times 2 to the x, and that gets you 2 to the x plus 1. And then plus 2 to the x times x squared times natural log of 2. And you could just simplify this to get x times 2 to the x power times 2 plus x to the natural log of 2. And this is just a simplified form, but essentially this is the derivative of 2 to the x plus times x squared. Now we have a lot more complicated function, x squared, e to the x times cosecant of x minus 3x squared. So using the sum rule always comes first, because that using PEMDAS, actually no, not PEMDAS. The sum rule comes first before, it's a reverse PEMDAS actually. So the sum and difference rule come before product or quotient rule that we'll see before next. So First, we separate the different equations. You get the derivative of e to the x times cosecant of x minus the derivative of 3x squared. So we can see that the derivative of 3x squared is 6x. But you can use the product rule to find this derivative here. And that'll just get you e to the x times the derivative of cosecant of x plus cosecant of x times the derivative of x e to the x. And then this will just get you negative e to the x cosecant of x times cotangent of x plus e to the x cosecant of x minus x 6x. And then you just have this big equation here. Don't worry about the big equation, but all you need to memorize is just what the product rule is. It's just the basic fundamental of the product rule. Lastly, we're going to talk about the quotient of two functions. So if we have f of x divided by g of x, the derivative of that is just g of x times the derivative of f of x minus f of x times the derivative of g of x, all over g of x squared. So unlike the derivative of the product of two functions, this order matters in this. F of x is in the numerator and g of x is in the denominator, so you have to differentiate between those two functions. So it's always the denominator function times the derivative of the numerator minus the numerator function times the derivative of the denominator function, all over the denominator function squared. And this is also referred to as the quotient rule. So we could just use that here. So let's look at some examples here. The derivative of 10 to the x power over x. So 10 to the x is the numerator function, and x is the denominator function. So remember the exact positions of where each function should go on the derivative. F of x is 10 to the x, and g of x is x. So you have 10 to the x power times the derivative of x minus x times the derivative of 10 to the x, all over x squared. So you just have the denominator and then square that. So then the derivative of x is just 1, and the derivative of 10 to the x is just 10 to the x times natural log of 10. So then you have 10 to the x minus x times 10 to the x power times natural log of 10, and then you just simplify that to get 10 to the x of 1 over x squared minus natural log of 10 over x. Now, if we have, this doesn't look like a product function yet, but we can manipulate it to be a product function. So we can see that we have this derivative here. So the derivative of natural log of 5 over the natural log of x. Now this is a product. This is a quotient function. So the numerator is natural log of 5. And the denominator is natural log of x. So we get natural log of 5 times the derivative of natural log of x minus the natural log of x times the derivative of natural log of 5, all over natural log squared of x. So the derivative of natural log of x is 1 over x. And notice that natural log of 5 is a constant. So the derivative of natural log of 5 is 0. And then 0 times anything is 0. Any non-zero number is 0. So you get this whole term becomes 0. And that you can see that here, that all the previous terms cancel out. And then you get the natural log of 5 over x times natural log squared of x. So now we're gonna review what we've learned so far. We've learned about the definition of the derivative. We've learned about the derivatives of fundamental functions, mainly the power function, exponential function, logarithm function, trigonometric function, and the piecewise function. And we talked about the derivative rules and properties of differentiation. So we have the constant times the function, the sum and difference of two functions, the product rule, and the quotient rule. So thank you for watching my video. And if you have any questions, please email me at this email. And the next video we're going to talk about is unit 3, which talks about the second part of differentiation, or which talks about the composite, implicit, and inverse functions. So we're going to talk about that next video. So yeah, thank you for watching, and I hope you have a good day.